Hello everyone, myself Siksha. I am from Chemistry Honors final year. Today I am read the chapter Spectroscopy from the book Organic Chemistry published by Pardeeps. Spectroscopy nuclear magnetic resonance. During the last 6 decades or so, spectroscopic methods such as ultraviolet, infrared, nuclear magnetic resonance, and mass spectroscopy have emerged as powerful tools for identification and structural determination of organic molecules. The ultraviolet and infrared spectroscopy have already been discussed in detail. Therefore, in this unit, we discuss nuclear magnetic resonance spectroscopy, which was discovered by Felix Bloch and Edward Purcell in 1946. The field of NMR spectroscopy has been further divided into a number of subfields depending upon the magnetic nucleus being examined. For example, proton magnetic resonance (PMR) or HNMR, carbon magnetic resonance (CNMR), fluorine magnetic resonance (FNMR), phosphorus magnetic resonance (PNMR), etc. However, in this unit we will discuss only proton magnetic resonance and the base principle of NMR spectroscopy. Magnetic properties of nuclei. Like electrons, the nuclear particles, protons and neutrons are also considered to spin about the axis. Further, like electron, each proton and neutron has a spin quantum number 1 by 2. If the protons or neutrons in a nucleus are not paired, the nucleus as a whole will a resultant nuclear spin. Numerical value of this nuclear spin quantum number I depends upon the number of protons. Numerical value of this nuclear spin quantum number I depends upon the number of protons and nuclear having parallel and antiparallel spins. It is related to the mass number and atomic number as follows. ये आप दिखा रखा है यहाँ पे. In agreement with the above general rules, न्यूक्लियाई सच जैसे प्रोटॉन हाइड्रोजन का दिखा दिया, कार्बन नाइट्रोजन फ्लोरीन फॉस्फोरस एटसेट्रा. It is fortunate for organic chemistry that and oxygen 816 are non-magnetic, otherwise the NMR spectra of organic molecules would have been complex. Now, since an atomic nucleus is associated with charge, therefore like any other rotating charge, it generates a magnetic field along the axis of its spin. Therefore, such a nucleus behaves as a teeny bar magnet and has a characteristic magnetic moment mu. Nuclear spin states. When a nucleus with I more than 0 is placed in an external magnetic field, it is found to have a set of discrete orientations with respect to the applied magnetic field. These various orientations are referred to as a spin state. For a nucleus with spin quantum number I more than 0, there are 2I plus 1 allowed spin states which differ from one another by unity. That is, the various spin states are given by minus I plus I this. As follows. Thus, if it follows that nuclear spin states like electronic and vibrational states are quantized, for example, a proton hydrogen nucleus with I is equals to 1 by 2 has two allowed spin states designated as minus 1 by 2 and plus 1 by 2. For chlorine with I equals to 3 by 2, there are 4 allowed spin states. This designated as minus 3 by 2, minus 1 by 2, plus 1 by 2 and plus 3 by 2. In the absence of a strong external magnetic field, the nuclear spins of magnetic nuclei are oriented randomly. However, when these magnetic nuclei are placed between the poles of a strong magnet, they either align with the field or opposite to the field. You can see the diagram. When a compound containing hydrogens and therefore protons is placed in an applied external magnetic field, the protons may assume one of the two possible orientations with respect to the external magnetic field. These two possible orientations spin states do not have the same energy and hence are not uh, equally populated. The orientation in which the spins of the nuclei magnets are aligned parallel to the external magnetic field is slightly lower in energy and hence this spin state is slightly favored over the other orientation. I equals to minus 1 by 2, in which the spins of the nuclear magnets are aligned anti-parallel to the external magnetic field. The difference in energy between the two spin states is designated as delta E. In general, the value of delta is very small, but the magnitude depends upon the strength of the applied magnetic field as shown in figure. From figure 2.3, it is clear that when H not equals to 0, delta E equals to 0. That is, in the absence of magnetic field, the two spin states of a proton have equal energy. However, as the strength of the applied field increases, the energy difference between the two states increase. At a field strength of 104100 G or 1.141 T, delta E 2.3 into 10 k minus 5 kilojoule mole inverse, while H naught this etc. Principle of nuclear magnetic resonance. To understand the principle of nuclear magnetic resonance, let us consider the motion of a common spinning top. When the spinning top is distributed a little, its spinning axis will trace out a circle perpendicular to the Earth's gravitational field, as shown in figure 2.4. Such a motion is called precession. Now, in a similar way, when a nuclear magnet is placed in an external magnetic field, it will experience a torque force perpendicular to the axis of the nuclear magnet, which will tend to align it with the field. Since the nuclear magnet is spinning, it will not align with the external magnetic field but will precede around it with a certain angular frequency omega, called precessional frequency, or the laminar around and the laminar frequency. The frequency at which a proton will precess will depend upon the strength of the applied magnetic field. Stronger the applied magnetic field, higher is the precessional frequency. For a proton, if the applied magnetic field is this gas, the precessional frequency will be 16 megahertz. Since a proton has two allowed spins state I plus 1 by 2 and minus 1 by 2, it can precess in two principal orientations, one aligned with the applied field low energy and the other opposed to the applied field high energy. It is possible to induce transitions between these two orientations by irradiating the preceding nuclei protons with radio waves, electromagnetic radiations of correct frequency. When the precessional frequency of the nucleus is exactly equal to the frequency of the electromagnetic radiations, the absorptions occur and the nuclei in lower spin state flip to the higher energy spin state. When this occurs, the nucleus and the radiation of frequency beam are said to in the resonance, and since this resonance is due to the magnetic properties of the nuclei, it is called nuclear magnetic resonance, abbreviated as NMR. The exact amount of radio frequency energy needed for resonance depends upon the strength of the external magnetic field and on nucleus being irradiated, that is delta E equals to h nu y h upon 2 pi h naught. Where delta E equals to energy difference between the two spin states, h Planck's constant, gamma gravimetric ratio. It is a ratio of magnetic moment to angular moment and it is constant for each nucleus. For a proton, the value of omega equals to 26,750. It may, however, be noted here that an NMR instrument with a magnetic field strength of 1.41 T and operating at a constant RF of 16 MHz can introduce transitions only among proton spin states in a molecule, and it is not useful for other nuclei. Therefore, separate instruments are required to observe transitions in the nuclei of other elements such as carbon, phosphorus, fluorine, etc. However, the modern, more expensive fluorine transform instruments which are commonly used these days can be used to observe the resonance of nuclei of several different elements in a single instrument. Instruments with 200 and 300 MHz are now quite common, and instruments with frequency up to 800 MHz are found in the advanced research institute and bigger universities. We have discussed about the energy difference between the two spin states of proton at 60 MHz as just 2.3.9 into 10 minus 5 kilojoule mole inverse. Since this energy difference is too small, thermal energy due to room temperature is sufficient to populate both the spin states. There is, however, a slight excess of nuclei in the lower energy spin state. The magnitude of this difference can be calculated by using Boltzmann distribution equation. The following equation gives the Boltzmann ratio of the nuclear spins in the upper and lower state. N upper upon N lower equals to E minus delta E upon KT, where delta E is the energy difference between the upper and lower spin states and K is the molecular constant या फिर gas constant. Using this equation, we can calculate that at 298 Kelvin for an instrument operating at 60 MHz, there are 1 lakh nuclei in the lower spin state for that occupy upper high spin state. In other words, in approx 2 million nuclei, there are only 9 more nuclei in the lower spin state. These excess nuclei are the ones which are responsible for the NMR signal. When the 60 MHz is applied, it is not only transitions. Thank you.